All right, in this video, we're going to talk about the forces and torques on charges, and then charges, current carrying wires, and magnetic dipoles. So basically forces on the first two, charges and currents, and then torques on magnetic dipoles. So this first section focuses on the first of those three things, the force on a charge. So there's a few things that motivate the formula, the main formula of this section. So first of all, if a charged particle is moving, if a charged particle is not moving, then it does not feel a magnetic force. So this picture right here. So V equals 0. So even if the charged particle experiences a magnetic field, it still doesn't feel a force. And this is very different from the electric field, an electric force, right? So this is another indication that the magnetic field just acts very differently from the electric field. Another interesting thing is that if the positive charge moves in the same direction, either parallel or anti-parallel to the magnetic field direction, then the force is also 0. So the only way that you have a non-zero magnetic force on a charged particle is if some component of its velocity is perpendicular to the magnetic field. So what your book has done here is, so whatever the velocity is, it's not parallel or anti-parallel to B, because in that case, the force would be 0. So what your book has done is drawn a plane that goes through the velocity vector and the magnetic field direction vector. So that defines a 2D plane, and the force is perpendicular to those two vectors always. So your book defines that plane and then draws the direction of the force for a positive charged particle. But we also see that a negative charged particle will have a force in the opposite direction for the same velocity and the same magnetic field. So you'll notice here that if a positive charge is moving in this direction and the magnetic field is in this direction, the force is in the direction of V cross B. So again, take your right hand, fingers towards the direction of V, curl them towards B, and your thumb is pointing in this normal direction, not the other one. And that force actually gets bigger the bigger the perpendicular component of the velocity is. So this force is actually proportional to the velocity, but only the perpendicular component of the velocity. Right? Any components that are parallel to the magnetic field don't count. So the force is greatest when they're perpendicular to one another, as we might expect from this statement. So we can sum up all of these things that we see in nature with a single formula, and that is this. The force on that charged particle in the presence of a magnetic field, the magnetic force on that charged particle, is QV cross B. So like I was saying, it's the force is in the V cross B direction only for a positive charge. For a negative charge, you have to find the V cross B direction and then flip it to get the force on a negative charge. So one way is to actually cross these two vectors, fingers towards V and curl them towards B. There's a shortcut that sometimes people use, and that is to have your thumb in the direction of so for a positive charge, you use your right hand. You have your thumb in the direction of the velocity, your fingers in the direction of the magnetic field, and then you could either have your finger pointing up out of your palm, or the direction out of your palm is the force on that charged particle. So then you either have to flip that direction if you have a negative charge, or maybe you have to start it with your left hand. But I'm going to get away from that. I think it can get too confusing if you have too many different kinds of rules. I'm going to just stick with, fingers in the direction of V, curl them towards B. If you have a positive charge, that's the direction. If you have a negative charge, you have to flip it. So just appealing straight to the formula. Cyclotron motion. So the force is always perpendicular to the velocity for a charged particle. And as a result, the magnetic force doesn't do any work on that charged particle. So the particle doesn't speed up or slow down, and in fact, it will go in circular motion. If there's a component of the force of the velocity vector that's parallel to the magnetic field, then it's going to sort of drift along that direction, but then also move in a circle. So it'd be more like a helix. And actually, our example problem is going to cover that. So the charged particle moving around in a circle has a corresponding cyclotron frequency. So we can actually get a formula out of relating some of the quantities in this picture. And the key insight to get this formula is to see that, well, if the force is always perpendicular to the velocity, so then the velocity is going to start to turn, the charged particle is going to start to turn. And if it's constantly turning, like say to the left in this picture, then it's going to wind up moving in a circle. And the force is always towards the center of the circle. So the magnetic force we can set equal to the centripetal force. That's the key equation that we're going to start with and then just manipulate it until we get some other quantities. So that's what we have right here. So the magnetic force is QV cross B. If V is perpendicular to B, then this simplifies, and we can just say QVB, right? Because sine of the angle between them, sine of alpha up here, would be 1, because alpha would be 90 degrees if V is perpendicular to B. So this is the magnetic force if V is perpendicular to B. And this is exactly what your book is plugged in right here. So here V has to be totally perpendicular to B. It's just the perpendicular component. And we set that equal to mv squared over r. And so what you get is that this is the radius of the motion of that charged particle. Notice how, like, the stronger the magnetic field, the smaller the circle, which kind of makes sense because it's a bigger force. But it's also inversely proportional to the charge to mass ratio of the particle. So for example, a electron versus a proton have the same charge, but much different masses. So the proton with a much bigger mass would have a much bigger radius of this thing. So if you had an electron and a proton moving at the same speed, the electron is going to have a much smaller circle than the proton, by a factor of about 2,000. So that's the radius of the orbit. You can rewrite quantities in terms of what's called the cyclotron frequency. So number of revolutions, number of cycles per second. How many times does this particle move around in a circle per second? That's the lowercase f. So it's this speed divided by the distance. Right? Meters per second divided by meters gives you 1 over seconds. It gives you how many cycles per second. So you can rewrite this formula in terms of the frequency, and you get this formula, which is independent of the speed of the particle. So it still depends on the charge to mass ratio, but no matter how fast that particle is moving, it takes the same amount of time to get back to do 1 full circle. The radius of the circle depends on the charge to mass ratio, but it doesn't depend on the particle speed. And your book talks about, there's a practical application of this in accelerating particles called the cyclotron. The Hall effect is an interesting application of forces on charged particles. So you'll notice that, like, the way we've been talking about current, these two have been identical, like a positive charge moving to the right or a negative charge moving to the left. But you'll notice in reading this section that there's a difference here in these two pictures in the Hall voltage. So in other words, which side is at higher electric potential, the top side or the bottom side. We've only been talking about the electric potential between these two sides, which is what's driving the current in the first place. But actually, because of the magnetic force, these charges so like a plus charge that's moving to the right, in the presence of a magnetic field, could feel a force in the direction perpendicular to the direction it's moving. It's like, so a plus charge, if the magnetic field is pointing, so it looks like out of the page, right? Because these dots right here. So if the magnetic field is pointing out of the page, take your right hand, point them towards V, curl them out of the page, and your thumb points down. So what happens is that positive charges start to accumulate on the bottom here. That's why you see the plus charges there, leaving a minus charge up here. And this keeps happening. The positive charges build up until positive charges don't have any desire to go down anymore. So in other words, the electric field cancels the magnetic field. If you look at a minus charge, actually, if the negative charges are the charges that are moving, then actually it's the minus charge that goes to the bottom for the same magnetic field. So you'd build up a Hall potential difference that's opposite in sign. So this can help us figure out what things are actually moving in the conductor, positive charges or negative charges. Okay, magnetic forces on current carrying wires. So currents ultimately are positive charges moving, positive or negative charges moving. So we can just say it's positive charges moving up. So as a result, like we can use our result from the previous section. You know, remember if a positive charges move, if a positive charge moves in the direction of the magnetic field, it doesn't feel a force. It has to move in a direction perpendicular to the field. So for this wire, there's no force. But for this one, there is, because positive charges are moving up, magnetic force is into the screen. So take your right hand, fingers up, curl your fingers towards the screen, and you get that your thumb points to the left. So force is to the left right here. Now with currents, we normally talk about the current in the wire rather than the charges themselves. So instead of QV cross B, sorry, for the force, V is like length per unit time. And if we just move the time over to the charge, charge over time times length cross B is the magnetic force. So this right here is current. So this helps motivate this formula for the force on a current carrying wire. It's the current times the length of that current segment. So IL points in the direction that the current is pointing for that wire. Cross B gives you the force on that wire. And so between two parallel wires, so the overall result is that if the two wires have currents pointing in the same direction, they're attracted to each other. But if they're pointing in opposite directions, they're repelled by each other. And the way you would analyze this is you take the magnetic, okay, so this wire creates a magnetic field at the location of wire 2. So that's what these X's are. So the first wire creates a magnetic field here, and you can calculate this is, so B at the location of wire 2 is mu naught I over 2 pi r. The current in wire 1 over 2 pi r. So then you take the magnetic field that's here at the location of wire 2, and you plug it into this formula for I2. So the force on wire 2 would be I2, the length of wire 2, times the magnetic field at the location of wire 2, but due to wire 1. So if you do that, you can prove the force between the parallel wires is this right here. And notice how it's symmetric between I1 and I2. It has to have the same magnitude for the two, which makes sense from Newton's third law. So the force from 1 on 2 has to be equal and opposite to the force on 2 from 1. I think I said that in the right order. Reversing the numbers. Okay, the final section has to do with forces and torques on current loops. So for the force between current loops, we've already sort of seen this because remember a current loop acts like a bar magnet. So for example, this picture right here, we could redraw as this sort of bar magnet, right? The current's coming out of the screen at the top right here and into the screen is going into the screen right there. So if we imagine a circle right there, a circular loop of current, and we use our right hand rule, have our fingers going along that current direction, our thumb is pointing to the right. So it acts like a little bar magnet where it's setting up a magnetic field pointing to the right there. So this, and it looks like this other one right next to it is a bar magnet that looks like this. And if you have these two bar magnets, they seem to attract each other. North next to South Pole, they would attract each other. So you just have to redraw these in terms of like bar magnets to see whether they attract or repel each other. Okay, the torque on a current loop. So if you have, by the way, this discussion here is going to be very similar to dipoles in an external electric field. So remember that the P vector, the electric dipole moment, wants to line up with E. So we have the same thing here. The magnetic dipole moment tau vector wants to line up with B. So in a uniform magnetic field, there's no net force on the magnetic dipole moment on the current loop, but there is a torque, and there's a torque such that this mu vector wants to line up with B. So B is pointing in the plus Z direction. This mu, which is summing up the overall current loop, is going to want to line up with B, and the magnitude of the torque is mu B sine theta. You can use this fact to your advantage for an electric motor. So a motor will turn electrical energy into mechanical energy. So we have a battery right here, and the battery is going to keep switching directions for the EMF source. So just by switching which wire is connected to which side right here, we can keep switching the current direction. So the current is one direction. You know, you have mu, which is pointing in this direction. So we want it to point in this direction in order to get the current loop to rotate this way, to line up with the magnetic field that's pointing from the north to the south pole. So this is the magnetic field. Mu is always going to try and line up with B. And we want this thing to speed up. So mu is going to want to line up with B. As soon as it overshoots B, normally it would slow down. But if we reverse the current direction, reverse the current direction right when that happens, then it will speed up and go to the other side, and then reverse the current direction there, and it will speed up and go to the other side. So we can get this to spin around faster and faster if we keep switching the current direction. See, there are these little gaps in the piece of metal right here in order to flip that direction. Okay, so going over this example problem, remember that so we have a magnetic field, and we have a charged particle that's moving not just perpendicular, not just parallel to the field, but actually it has both components. So if we call this, if this is the speed, then we have components parallel to the magnetic field. We'll call it V parallel. Looks like it's V naught sine theta, sine of 30 degrees. And V perpendicular is V naught cosine theta, sorry, cosine 30 degrees. So we know those numbers, so we already know what this is and what this is. Right? So I'm just going to solve this algebraically, but we know what those two velocities are. So find the radius and the pitch of the electron spiral trajectory. So we actually talked about the formula for the radius, and it's right here, the radius of the cyclotron motion. So the radius is the mass, because we're talking about an electron here, will be the mass of an electron, times the perpendicular speed is what's relevant here. So the perpendicular speed of the electron, divided by the charge of the electron and the strength of the magnetic field. So we know all four of those quantities that we can compute right there. And then for part B, for the pitch. So it looks like from this picture, the pitch is how far like these, so if this thing is a helix, the pitch is how far away one loop is away from the next one over. So to figure this out, we're going to need to find that out. We're going to need to know how fast it's moving in this direction, in the Z direction, as well as how much time it has before it goes around to the same spot. So in other words, the pitch is going to be delta Z for one orbit. So it looks like this is, so distance is velocity times time. So this is how fast it's moving in that direction times the time for one orbit or one period. Or V parallel times one period is 1 over the cyclotron frequency. And if we look on the right here, looks like the cyclotron frequency we can just plug in. So the pitch is V parallel times Q times B over 2 pi m. So this is mass of the electron, and for Q, I'm going to plug in the charge of an electron as well. So it looks like we have both of these in terms of the given quantities.